Hey, Calc class, we're going to finish up these notes for derivatives of inverses, and the last method that we need to take a look at, they're just calling it method 3. Basically, it is the same process as method 2, but they just kind of give us a streamlined formula for it. The hardest part, this formula does look a bit confusing because of the notations that are in here, but I just want to break this down and refer back to the way we did it with implicit differentiation, and then hopefully this formula kind of makes a little more sense. Okay, so the way you would read this is, so remember the process, what we're doing, we're taking the derivative, the derivative of the inverse function of x at some specific value for x. Okay, and according to this formula, what it is it's 1 over, and remember 1 over because we noticed that the derivatives were always reciprocals of each other at those reflective points from the function to its inverse, right? They were reciprocal slopes, basically, of those tangent lines. And so what we have to do is we have to take 1 over, and this reads f prime of f inverse of x. So it's 1 over the derivative of the original function, but evaluated at that reciprocal, or I'm sorry, at that reflected point, right? So this is where we basically went and looked for, the y coordinate when we looked at the table of values, and we said, okay, yeah, we're going to use that x value there, and that's what we need to plug in. Okay, so I want to just take this formula and go back up and just kind of compare that to what we did here in example 4, right? So we found the inverse by basically just interchanging, f of x was y. We interchanged x and y right here, right? And then we did the derivative of it. Okay, so we did the derivative of our inverse. That's what we have right here. This is our derivative right here of our inverse. So the derivative was the 3y squared minus 8y plus 7. That was the derivative of the inverse, right? And then we had 1 over that because when we solved, we had to factor out that dy dx. And on this side, we always have a 1. So, when we end up solving that, we have a 1 over. So if you compare that back to what we have here, it's the same thing. It's 1 over. This was our derivative of our original function, right, in terms of y, and then evaluated at a specific point, right? And to get that point, what we did before was, we graphed it on the calculator, and we said, oh, okay, we're supposed to evaluate x equals 3. Well, on my original function, okay, that means my y coordinate's going to be 3, and I saw that I had the ordered pair like 1, 3 on the original function, which means that 3, 1 is going to be on the inverse, right? And so because I had to put a y value in there, 3, 1 was the point on the inverse, and so I plugged the 1 in, okay? And then I was able to get the derivative of the inverse at x equals 3, which was here, but I had to use the y coordinate, okay? Same idea right here. We're going to be using that y coordinate on the inverse, okay? And I'm going to walk us through what this means, okay? I'm actually going to come back to example 6 because that one's maybe a little harder to get the main idea of what we're doing here. So I want to go to one that just has like a polynomial like this one, probably a little more common. Okay, so this was our formula. It was f inverse prime of x, so that's just the derivative of the inverse of x, and we're going to be doing it at x equals 3 on the on the inverse function. Okay, so here's our formula: 1 over f prime of f inverse of x. Okay, so what we're trying to do at x equals, so really what we're doing is we're doing, same notation, I'm just saying at 3 because that's what they're telling us. We're evaluating the derivative of the inverse at 3, right? So I have to do 1 over, and just kind of following this notation, f prime of f inverse of 3. Well, what does this mean? What does f inverse of 3 mean? Okay, well, let's think about this. Okay, so I'm just gonna pull up this graph of our original function, right? And when I pull it up, we're gonna see that the point 2, 3 is on there. Okay, so this is what I've got. This is the equation. It was 1/4 x cubed plus x minus 1. And the graph looks like that. So it's strictly monotonic, has an inverse. Okay, so if I pull up the table, okay, remember what I'm looking for here, because I'm evaluating it at 3, I want to look on my y column and I'll say, okay, where's 3? Oh, there it is. So actually the 2 is what's important, because here's what we're saying. If 2, 3 is a point on the original function, then 3, 2 is a point on the inverse function, okay? So that's what I'm writing over here then, okay? 2, 3, f of 2 equals 3, because when I input 2, I got 3 on that function, which means f inverse of 3 equals 2, right? Because they're always reflected. So input, output, input-output on the inverse function, right? And so that f inverse of 3 is what I'm putting right here, right? Which is going to be a 2, okay? F inverse of 3 is 2. Basically what it is it's the y coordinate on the inverse function, okay? Go back up here real quick, right? We needed a y coordinate on the inverse function, right? Because that's what, when you do it implicitly, you have y's there. So that's what we got. It's the y coordinate on that inverse function, okay? That 2, that's what's important right there. You never plug in this number on these problems. You always plug in the one that goes with it. So pulling up a table of numbers is important, and actually we'll get to that on example 8. Usually they just give you a table. Okay, oops. All right, so here's what I need then. All right, so I need to do f prime of 2 now, right? Because f inverse of 3, we've established that that's 2. So I need to do the derivative of my original function, just like what I was doing before. And then instead of it being in terms of y's, they do this notation, which is telling me put in that y value there, which was the 2, okay? So I do the derivative here. I should get, my power rule, 3/4 x squared plus 1, the negative 1 disappears. So here's what I've got. Okay, now so to finish this off, what I'm going to do, it's going to be 1 over, and then I just need to plug in, so f prime of 2, right? That's, yeah, I suppose I can do that right here. F prime of 2 is going to equal 3/4 times 2 squared plus 1. And so what do I get there? So that's going to be 4, cancel, that's 3 plus 1. This should turn out to be 4, right? When I figure that out. 3/4 times 4 is 3. 3 plus 1 is 4. Okay, so my answer to this is just going to be 1/4, okay? Because f prime of 2 is 4, so 1/4. All right? So hopefully that, you can follow the work on that. These reflected points are really, over the line y equals x. 2, 3 was on f, so 3, 2 is on f inverse, okay? And so that's telling me I got to use that 2. That's what replaces f inverse of 3 is the 2. So I just do the derivative, evaluate it at 2, and then I've got that reciprocal, okay? Example 6 was probably not as, I don't know, didn't help for the understanding, I didn't think, as much, just because, as it turns out on this trig function, the ordered pair pi turns on there. So when you flip it over, you still get pi, so f inverse of pi is also pi. So it was more confusing, I thought, to explain it on this one, but it's just the way it works out. So same formula, derivative of the inverse is our formula that we've got here. So it's 1 over, the derivative of f inverse of x, and we're doing it at pi. So f inverse of pi, which still turns out to be pi because it ends up being the same x and y coordinate on the original and on the inverse. So this way, I still take the derivative of what I've got here. So f prime of x, derivative of that would be 1 plus, and then derivative of sine would be cosine. And I'm evaluating that at pi, right? So 1 plus cosine of pi. And cosine of pi is -1, if you remember that. And so you've got 1 plus -1, which is 0. So as it turns out, this one ends up being undefined because you get 1 over 0. So it wasn't a great, I don't think it wasn't a great example, but we can see that one turns out to be undefined. Okay? Okay, so actually this one right here, number 8, this is a really important example because honestly, the questions I've seen on AP exams, they don't do a lot of, there might be something, occasionally, but I see these ones a lot on there. When they're going to ask about derivative of an inverse, they almost always do it in a table form, which makes it really actually pretty easy because they're telling us, okay, don't worry about it, it's strictly monotonic, it means it has an inverse. We're going to tell you some ordered pairs on, some function values for the actual function and then on the derivative, right? And so they don't tell us anything about the inverse, but that's easy enough. If we've got ordered pairs, we can flip those around, and those would be points on the inverse, right? So the idea here, just like before, when it said add x equals 3, what we really needed to look for was, hey, where was that y coordinate 3? Oh yeah, that had a value of 2, right? So that was the important one, and so that's kind of what we're going to do here. We're going to say, okay, well, they want g inverse prime of 1, or the derivative of the inverse of g evaluated at 1. Well, that means that on our, they're telling us, function values for g here, we want to look for actually where the y-coordinate is 1 here, not where the x-coordinate is. So we go across here and we say, okay, here's where the y-coordinate's 1, right here in this column. And so basically, we're evaluating it at this point. Negative 1, 1, well, it'd be the 1, negative 1 on the inverse function. But this is what's important. Now they're telling us, if I evaluate the derivative right here, I get negative 1/5. Well, we know we have to do the reciprocal of that. That's really all you have to do then is look at this and say, oh, yeah, right here, but because, this is the original function, I need to do the reciprocal of that, right? And so I just need to say that that's -5. That's all there is to it. Basically, you just got to do the reciprocal of one of these values. And where do you do it? Well, you just look for the y-coordinate that has this input value, because on its inverse, that would be the input value. That would be the x-coordinate, right? Okay, so in this next one, just to kind of get the hang of this, all you have to do, right? Okay, I need a -3. Look in the y-coordinate, the function values, right? Go across here. Okay, there's -3. And so I'm working with this ordered pair on the original, which would be -3, 4 on the inverse. But all that's important is, hey, here's the derivative value right there. I have to do the reciprocal of that. This is the slope on the original function. The slope on the inverse is going to be the reciprocal of that. And so my answer to this is just -1/2. That's all there is to it. And these are, like I said, these are the most common problems I ever see on the AP exam, is these table ones. So basically, key is they give you this value, you're looking for that y-coordinate, just like I did when we did it on the calculator. I was like, okay, I got to find that y-coordinate 3. There it is. And then then I'm working with this. I need to input a 2, and I had to physically do it because I had the equation here. But on these ones, they just give you the numbers. They give you f prime of these, or g prime of these different inputs, and so it's real easy. All you got to do is flip it around to the reciprocal. Okay, so that's it. That's everything for this section and unit.